should be good to go. So today, to get straight to the point, we are going to be talking about what is arguably one of the most important parts about the computer science degree, or any of the nearby fields. If you're a computer science student, what have you, almost all the fields anywhere near computer science all rely very strongly on the principles that we're going to be talking about today and in the next few lectures. Honestly, these principles are often kind of expected by many students to be gained naturally as you go through the degree, just kind of figuring it out as you go. However, I find a lot of value in actually talking about them specifically and with purpose. So these are all going to be about. These principles all have to do with solving problems. Now, I am 100% sure that all of you, having gone through any amount of schooling, are well acquainted with solving problems. This seems to be all we get in school, right? The teacher, instructor, whatever it may be, gives you a problem, you have to solve it, all the way back from grade school, all the way back from, the 2+2 math problems you received. They gave you that 2+2 problem, and you, that little kid over there, were expected to solve it. You're expected to figure it out in your head and write it down on a piece of paper to prove that you could solve that problem, right? And that is the core of virtually every field that is in STEM, and to some degree, even some of the more creative fields. We are bombarded with problems constantly in this world and in life. That's just what they are. And we have become very adept and very used to solving them. The difference being between the steps we're going to be talking about today and what you are often used to is today we are going to be talking about how to solve a problem algorithmically. How to devise an algorithm that can solve a given problem. The difference being that, for example, you all got to class today. That was a problem you had. Doesn't seem like it, but that's essentially a problem. You had to come to class. To get here, you had to find the school, then you had to find the building, then you had to find the classroom. And then you had to find your seat, and you had to sit down, and you had to dread whatever was going to happen today, right? Like, that's all part of the process. And it's a problem that you're used to solving. You have figured out ways that you are good at solving that problem. You are used to using Google Maps, Apple Maps, whatever it may be, Yahoo, Wikimats, whatever. You are used to that. You are used to being able to use that tool to solve that problem. We are now wanting to apply that idea over to the field of engineering and computer science. Arguably, I know, most people believe that this degree is all about learning how to write code. And don't get me wrong, that is important. Knowing how to write code is important. However, that ability to write good code is greatly overshadowed by the ability to solve problems, right? That is why we write code. That's why you are learning how to write code. That's why you are going through the headache of learning things like syntax and learning how to handle inputs and outputs, how for loops work, how while loops work, how recursion works, how all these different algorithms work. That's the whole reason. They are all tools to be able to solve a problem, right? The same way that, for again, reaching back, Google Maps was a tool that you are used to solving the problem of knowing how to get somewhere. It's that same relationship. All these bits and baubles that we teach you about coding are tools for your toolbox to make it so that you are better at solving problems using code. Once we have figured out a solution to a problem, using whatever manner we're going to talk about later and whatever manner you all use, we all come up with, the point of code is to be able to automatically apply our solution that we managed to figure out to almost any scenario, right? We write methods that take in any two integers and return their sum, for like a super simple example, right? If we are given two integers, we can add them together and return the sum. We figured out how to do that, right? Like, we figured out how to take two integers, call the plus sign on them, and return whatever number that came out of that. We figured out that solution. So now we write code so that ourselves or anyone else can go ahead and use that to automate the solution to that problem. If they have that same problem and they're like, well, I just don't want to do it with this, like, oh, your solution worked. Can you do it with this input? And again, if it's good code, it should. If it's a well thought out solution, it should handle any scenario within reason, right? And that's the entire point. We're trying to automate our solutions that we managed to come up with. So it's almost like the code is secondary. The first part, and the most important part, is that we managed to solve the problem. Then we transform our solution into code so that we can use it and so we can let others use it to continually solve that problem forever. That's the awesome part about it. Our solution that we managed to come up with, these incredible, incredible pieces of software technology that people have managed to come up with, are essentially limitless. Someone solved that problem, and now we get to reap the benefits. All the way back from the beginning, someone figured out how electricity can be used within gates to create its own logic. And lo and behold, we have computers and the thing I'm using to record right now. It's incredible. And so, in order to get to these solutions though, a lot of students think that coding is not so much a byproduct, but the first and foremost thing that should be done. This is a trap. And it is the reason it's essentially the reason that you can go to a coding boot camp for 2 weeks during one of these summers, or 2 months, whatever it may be, and learn pretty close to the amount of coding you will be learning in this degree in those boot camps. Now, granted, we, in the computer science degree, we go a lot more in depth with some more, near the hardware level coding languages, but as far as like Java is concerned, you can learn basically everything we learn about Java in this degree in a coding bootcamp. You can. That's it. You can do that. Because that's not the point. We are not trying to teach you how to code here. We're trying to teach you how to solve problems and use code to automate those solutions. And so, in order to do that, you need an approach. Yes, by all means, you can guess and check your way through solving any problem. That is always an option. However, it is not a good one, and it is the reason it's the butt of the joke. Guess and check is valid in some scenarios, but generally speaking, solving a problem cannot be done through guess and check every time. You want to create a solution. And so in order to do that, you have to have some form of steps you take to get to that solution. A huge issue that a lot of, especially newer students have, newer coders have, is they see a problem, they get a problem, it's written out, and they say, okay, there's my problem, I've read it, and they open their laptop and immediately open up their IDE, Visual Studio, Eclipse, whatever it is that we're using at this point. That is bad. That is a trap, that is a huge issue, because it skips over so many parts of actually solving a problem that are way more helpful than what is essentially hard, not quite guess and check, but making it way harder on yourself by not giving any preparation or anything to use for making that solution, and rather just going at it with bits of code, applying Band-Aid solutions as you go and making it overall way more complicated than it ever has to be, every single time. As someone who looks at student code a lot, I can pretty directly tell when someone wrote code on the spot or when they figured it out and then wrote code for what they figured out. It makes a world of a difference. Not only in your code readability, but in how actually stable the code will run. And especially when problems get harder and harder and harder, your code needs to be more and more and more stable to actually work with it. And a problem that a lot of newer students have is they have this idea that like all this like preparation and planning and like figuring it all out beforehand and like I'm sure a lot of your CS professors have said, like writing tests before you actually write code. That's all some form of like training wheels for newer programmers so that you can get more comfortable in it. That is not true. That is a common thought, but it is flat out false. Whereas in fact, those planning and preparation methods are actually tools used by experts in the field to be sure that they have a good solution, a stable solution, and one that is almost trivial to transfer into code. The goal here is to solve the problem in such a way that the coding is not the hard part. So, for example, You've seen some simpler and harder problems as you've gone, and so for the majority of this section, we're going to be talking about, we'll talk about the Tower of Hanoi problem. Sure, some of you have heard of that, sure. Most of you haven't, but it's a game that I'm sure in some form or another many of you have seen, where there is a big flat plank and 3 spikes. The origin of this game actually comes from a really interesting fairy tale. Look it up if you're curious, but anyway. 3 spikes with a bunch of discs on one of the spikes of differing sizes. So there's 4 discs here, right? Biggest one, next big, and then the smallest one. The goal of the Tower of Hanoi game, or the problem, is to take the discs and move them to another peg by the time you are done, in the exact same order. However, the rule is, and the reason it's hard, is that you can only move 1 disc at a time. You can only move the top disc of any stack. So I could only move this smallest disc right here. Like let's say I moved it over to the middle peg. And you can never have a peg bigger than the peg below it. That is an illegal move. You cannot do that. You would have to move it over here, for example, if you wanted to move it. That's the problem. We're going to talk about this problem. Now, I'm sure if you're familiar with the game, you already know what the solution is. You know about the pattern. If you're not familiar, it's not easy, but I feel like some of you could probably figure it out before the end of this lecture. However, what if we had 5,000 wooden discs? Would any of you be able to tell me how many moves it would take to finish the game? Probably not, right? So this is an awesome job for coding. Because yes, you could technically write that out, saying if it's important. That is a lot of work. And so we can use our ability to code to automate that process, to automate a solution to the problem. So now our job is to solve this problem algorithmically, using pure logic, okay? So how do we start that? What's important in solving a problem like this? It's kind of a big abstract thing, right? It's not code. It's wooden blocks and some pegs. So where do you start, right? What is actually necessary to solving a problem like this? And I'm open to answers. What do? You are given this problem and told to code a solution in which I can tell you any number of those wooden discs and you tell me exactly how many moves it would take to finish the problem. Don't think about the solution right now. Think about how you're going to get there. Go for it. Yeah. Yeah, perfect. Knowing what it wants. That is such an important point. Know what it wants. Sorry for my bad handwriting. You need to know what the problem wants, right? You need to understand the question before you can give an answer. Yeah, go for it. Yes, yeah, I know. I kind of talked bad on it, but yes, that is still a very important part of actually solving this problem with code is writing the code. Perfect. Hopefully that's not too dim for you. Any other ideas? Yeah. Yeah. I like that. Verify it works. That's super important, right? There's a few different ways to verify a solution works. You can do it manually or you can make your code do it. Both those are really important, and we'll talk about both of those actually later. Any other ideas? Yes. Okay. Commenting the code. Now, I think that's super important and extremely valuable as far as code goes. I'll write it up, but as far as solving the problem itself, with or without comments, the solution will work. But I like this headspace. The idea that the code is kind of secondary to your understanding. Yeah. Yeah. Yes, an important part of solving something is figuring out how to solve it. That's entirely fair. And I'll keep that wording. I actually kind of like it. So, figuring out how to solve the problem. Okay. Any others? I actually have 5 here. Yeah. Clarifying. Oh, yeah. That actually falls under here really nicely. So like knowing what the problem wants, a lot of times, you may need to clarify with your, the user or the buyer or whatever it is often called, the instructor more often than not, but you need to clarify what you actually need to do. So I'm going to add that kind of up here. Clarify. Yeah, that's a good point. Any other ideas? These are solid. No? Okay, cool. So I really like these. These are actually going to tie in really well to the process that we're going to be talking about. Solving a problem is so important that a lot of time and a lot of resources have gone into figuring out how to do it better and better and better and better. The process I'm going to talk about today, and that we're going to be focusing on for the next few lectures, is adapted from a book called How to Solve It, written back in the 40s by a mathematician from Europe. I'm almost always going to say his name wrong, but George Boya? He was a great mathematician who realized that teachers were not very good at actually teaching students. They were really good at sharing information, but teaching was a different ballgame. So he actually devoted a lot of work to it, and one of his main contributions is this How to Solve It book, which had a few-step process that he believed is integral to helping any younger student be able to solve a mathematical problem. Those steps have been adapted over and over again for many different fields, including CS, surprise, surprise, and engineering in general. Professor Jensen here at the University of Utah made an adaptation that he felt was solid and good for being able to solve problems algorithmically. And I adapted it very slightly, just to widen its reach a little bit. But it's basically his adaptation of that How to Solve It book. And so I'm going to keep referring to it as the 5 steps. And hopefully this marker doesn't die. So, 5 steps. First step, number 1. Understand. The first thing that you have to do whenever you receive a problem that you're trying to solve is understand that problem. Sounds kind of straightforward, right? But you would be amazingly shocked at how many students and how many people, professionals, whatever, seem to ignore this step. They read it and they're like, got it, and then they start working. But they're not always very good at actually verifying they understand what the problem's asking. Relates really well back to here. I'm going to put a little 1 tag by. Knowing what the problem wants and clarifying it if you need to is so important. You need to understand every single part of the problem and how it applies to your solution. The Tower Hanoi game. I'm going to redraw some of these pegs. The Tower Hanoi game has this like arbitrary tower, discs, and pegs and everything. Does super high level. Does this baseboard apply to your solution? Yeah. No, yeah, that's a really good point. Kind of, in the fact that it represents the bottom of these pegs, but the pegs themselves have a bottom, and you know you can only take from the top. So there's nothing in code that cares about this baseboard, right? Like that's not part of the problem. Does the whole idea that like these are discs, which are circles, and these are like pegs, does any of that really apply? Not really, right? Doesn't really apply. And so That stuff all is important to know about, but understanding how it applies to your problem is almost more important. Understanding how the idea of disk sizes actually applies to your code, that's important, right? So that first step, understand. How does it apply? What does it mean? All right? Once you figure that out, step 2, identify. This step, essentially, is identifying any tools you already have that will aid you in solving this problem. Like I said earlier, a whole portion of the CS degree is dedicated to giving you more tools. We teach you about all these different types of tools like code syntax, for loops, while loops, recursion, algorithms, searching, sorting, all these different tools to help you to be able to solve problems eventually. And so once you fully understood the problem, you can start to identify some bits and pieces of it that you already have an idea, or you already have something that can apply here. You've identified a part that you already have somewhat of an understanding of. The tower annoy problem. We're going to be moving disks over, right, in the very end. And as you come to understand the tower annoy problem, you'll see that as you move disks over, it's like moving this little disk to the center. We can't move this middle disk to the center. So the only possible move in this scenario is to move the middle disk over to the far end. And now we can't move this large disk to either of those because they would be bigger. We can't move this medium disk on top of the little disk because that doesn't make sense. We can't move it back here because that's just redoing what we just did. So the only reasonable next step would be to move the little disk on top of the medium disk, right? Interesting. Does anyone see what just happened? We had a stack of 3 over here, but if we forget about that bottom part, we had a stack of 2. Now that stack of 2 is over there. We just figured out how to solve the problem for a stack of 2. Move the little, move the medium, put the little on the medium. More or less. I think that this can continue to apply. Because now if we move the little back on the big, and then move the medium over, we can now move the little back, and keep on doing that, and eventually move the third plate over. We've made it possible for us to move the big plate. And now we just need to rebuild the tower. So I think what we found is that this is a recursive problem. If we can solve a smaller portion of it, we just need to solve the next step, and solve the next step, and solve the next step, all of which are the same. Or in general have the same ideas. So we can identify that this problem has something to do with recursion. And we know about recursion. You may not be comfortable with it, and that is fine, but you know about it. And that's important. That's the whole point of identifying. After you've identified what you know that could apply, you move on to what is arguably one of my favorite parts. Mostly because I just love the word. Sketch. Sketch. Sketching out an idea. And when I say sketch, I do not mean sketch as in a rough outline. That is fine if that's all you get to. But sketching a solution is all about actually devising a way to solve the problem manually. Ideally using nothing but pure logic, because eventually that's what your code needs to do. The sketch step is all about, okay, I know what the problem wants. I have some ideas of what could apply. Now I need to try and manually work at it to figure out how to solve, for example, how to just solve the stack of 3 problem. Or like we did, how we just solved this stack of 2 problem technically. We'd be like, okay, well I can do that. So now I understand I can move this big one over, like I'm supposed to do at the end of the game, is move the big one to a different peg. And now I just need to move this 2 stack again. I already know how to move a 2 stack. I move the little one over on its own, and then I move the medium over to the peg the little one isn't on, and then I can move the little one back on top of it. Oh, look, we solved the 3 peg. Anyway, the 3 disc one. Anyway. Okay, well, what if there was 4? I just have to solve the 3 and then solve the 4. You start to figure it out manually, all right? And as soon as you can start doing it over and over again manually with different inputs, that's when you're done sketching. You have a working manual solution. It may take forever, and maybe it's based on data that's so big that you can't actually step through it completely manually, but you know that it works. Once you figured out that it works, you should have a really good idea of what it should work on. Ideally every scenario, but who knows? And once you know what it works on, that means you're in a really good position to be able to pretest. Back to this point. Like a million of your CS professors have probably said, write the test before you write the code. That's what this is about. You understood the problem, you've identified the parts of it that you already know about, you've managed to figure out a solution. You've manually solved the problem. Now you need to turn that into code. However, to make sure your code works, you need to have some way to test it. And so, writing out the tests as soon as you figure out the manual solution will make it way easier later to actually code the problem. Because you'll have those tests ready and available. Every little bit you increment, you can have unit tests, for example, available to make sure that little part you wrote works. Because if you know this solution works, your code just has to replicate it, right? You don't have to worry so much about your algorithm being wrong at that point. You have to worry about just the code you're writing being wrong. So you can write your tests in such a way that you're like, okay, if I do this test manually, it worked. So this has to work on my code. If my code is failing this test, it is not because my solution's wrong, it is because the code is wrong. And that is so helpful. It's so much nicer than writing out your code and being like, okay, now I'm going to write some tests, and oh, this test is failing. Okay, this test is failing. So let me go look at my code and make sure it's actually working. I'm pretty sure that should work. Okay, what's the test want, right? If you write the test beforehand, you will know for a fact when you are coding that if your code fails a test, your code is wrong, not the algorithm. You don't have to recheck that the background thinking of your code is right. Because if every pretest you write passes the manual test, then you know it'll work. And then the last part, the part that everyone usually starts on. Code it. Code the solution. And we talked about over here, the second one, writing the code. I haven't been marking these, but writing the code out. I'm going to add some little addendums. Code /test /debug. Those are kind of addendums. And it's weird, right? Because that feels like the whole work in and of itself. That's usually all I do. Right? I got my problem and I write the code, then I test the code, and I debug the code. This is all one step. That's a big step, but it shouldn't be. It should not be that big of a step, right? The code should be relatively trivial. You've figured out a solution already. The testing shouldn't be hard. You wrote the tests already. And the debugging, again, should be pretty straightforward because you don't have to worry about your underlying solution being an issue if you're confident in your sketch. You just have to worry about how you wrote the code maybe later on. So even though it feels like code testing and debugging is a huge thing that should all be done at once, in reality, you've already done like all the hard work. You've solved the problem. You figured out the problem, figured out what you knew that applied, actually made a solution for it, figured out what scenarios should work with this solution. You just got to turn it into code. And I don't mean to downplay writing code. Code can be hard. Don't get me wrong. Like, I know I've been talking about recursion up here like it's nothing. Recursion can be hard. Recursion's weird. It can be really difficult. But you've done the hard part. You've solved the problem. Now just make the computer do it for you. Tell the computer what you did and make sure it does it too. That's the reason that in the sketch it's so important to try and solve it using pure logic, quote unquote. And when I say that, I mean solving the problem using simple comparisons, if statements, that whole idea of no intuition. You can't be like, well, this feels like it should go here, or something like that. That's not allowed. The computer doesn't feel that, right? So your sketch should be reliant on logic. And so once you've gotten to that part, you're done, right? You've taken these 5 steps and you've written an algorithm to solve a problem. Algorithm is like a big scary word, but it's essentially code that solves the problem. There's like an actual definition, but the easiest way to think about it is an algorithm is code that is made to generally solve a general problem. We can write code to generally say how many turns it'll take to move a stack of a tower of Hanoi problem, to move the entire tower over a peg, or like the opposite peg. Technically, in the game it doesn't matter, but either way, moving it over. And that's it. And so, for the next few lectures, we'll talk about each of these more in depth, with a small assignment before each, hopefully introducing you to it. And so this first assignment is going to be all about the understanding step, okay? This is really, anyway, it's an important assignment, it's an important step, and so please take it seriously. The first step is a little more fun though. It's kind of just an introduction to try and help you feel more comfortable with like what taking apart a problem looks like. And so, again, most of it will be, most of it will be graded on just your effort, not correctness. The second part will once again mostly be graded on effort, but there are some true or false questions that will be graded on correctness. But in general, try and focus as you're going through about what it's teaching you about how to better understand a problem. Okay? Sweet. Well, thank you so much. Hope this actually helped, and I'm excited to keep going over it all with you and actually really dive into the Tower of Hanoi problem as we go through each of these steps in more detail, because it's a fun problem. Other than that, thanks, Tim. Enjoy the rest of your days.